Okay, everybody, this is lesson 3.1 on symmetry. Chapter 3 is all about graphs and looking at different relationships in a graph. And so today we're going to talk about graphs that are symmetric or have symmetry in them. So there's different ways you can be symmetric. Think of the capital letter A for a second. If you think of the capital letter A, what symmetry does this graph have? Well, most people would say, well, if you fold it right down the middle, so think of that as your fold line, it's the same image on both sides. So if you fold it over, it lines up. And that's a really great example of a graph that's symmetric, has the same image on both sides when you fold it. Some people were saying when you look at a butterfly, if you fold it down the middle, that they're the same on each side. All that type of symmetry is called line symmetry. So when you fold it on a line, it lines up exactly. But that's not the only kind. There's also point symmetry. We're going to talk about that one today in 3.1. That's our first part. So point symmetry looks a little bit different. Then there are graphs that actually have both symmetries. They have both line and point. And then our last type of symmetry, or I guess type of graph, is graphs that have no symmetry at all. So they have none. And there's a lot of graphs that fall into that category. So our goal here as we move forward in the year is every time we look at a graph, a new equation, a new function, we can think about these things about the graph and what similarities or differences they have. And one of those things is symmetry. All right, so let's talk about what is point symmetry. Definition is going to bring you back to your geometry days here. So if you have 2 points, P1 and P2, super creative there, huh? They are symmetric with respect to, so I'm going to abbreviate that, SWRT. You're going to see this a bunch. That means symmetric with respect to, oops, no, I didn't write it out. It's just an abbreviation of saying what the symmetry is. You have to say symmetric with respect to something because you need to know, is it symmetric with respect to a line, a point, what line, what point? So they have a little bit better idea of what that graph means. So are symmetric with respect to a point, and I'm going to call that point M. So the point M is going to be, you're going to understand why it says M here in just a second. If and only if M is the midpoint of, see if you remember this notation, P1, P2 with the little line over the top, that means line segment. If it was going to be a regular old line, they would have arrows on the end. So line segment P1, P2. Let's draw a picture. That's a lot of geometry to talk about. So we have a point 1, a point 2, and there's a line segment connecting them. If M is going to be the point of symmetry, it has to be the midpoint, well, that means in the middle, of that line segment. So these two would have to be congruent. That relationship would have to be true on every pair of points on your graph. So if you had a point number 1, you would have a point number 2 always where you could draw that line segment from the first point through the midpoint and find a point equal distant on the other side. So that's what it means to be symmetric with respect to a point. Another way that people like to think of it is if you rotate your picture 180 degrees, the picture is the same. So that means you would have, if you rotate 180 degrees, point 1 would land on point 2, point 1 and point 2 would land on point 1. So it goes in both directions. So if you rotate 180, the picture is the, oh, I said is the same. There we go. So that's another way to look at point symmetry if that visual is a little bit easier for you to think of. All right, so let's look at some pictures first. You can understand what kind of graphs we're talking about here. Take the circle. So let's look at number 1. The place where we'd have symmetry with respect to a point would be in the center of the circle. That's where the M would have to be. Because if you take any point on the circle and draw a line segment through point M, which is the center, and go to a point on the other side, it will always be equal distant. It doesn't matter where you pick your starting point. Through the center, you're going to have a point equal distant on the other side. That's the definition of a circle, right? All points that are equal distant from a fixed point, which is the center. So these are symmetric with respect to the center. It has to be the center though, right? It can't be any other point. So this is a great example of a graph that has a symmetry point. That's actually not a point that's part of the graph. It's okay, it's in the middle. So when we think of point symmetry, the point sort of needs to be in the middle of everything that's happening because you have to have points on either side. All right, let's take a look at number 2. This is a graph you're going to see a lot of later in the year. Think about where the middle of that graph would be for you. Where would you consider the middle to be? When I look at that picture, I figure this looks kind of like the middle. It's halfway on the x-axis there. So if you pick any point on this curve, If you draw a line segment through that midpoint, you're going to find a point equal distant on the other side. That means that point M would be the symmetry point. Well, let's see if that works everywhere. What if you pick a point over here? If you draw a line segment through that midpoint, well, sure enough, there's a point on the other side. And you could do that for any point on that graph because the heights of those two curves are equal. So this is symmetric with respect to, using our abbreviation again, that point M. So it has a symmetry point as well. All right, let's take a look at graph number 3, our friend the parabola here. I'm just going to put arrows on the end. When you think of a parabola, most people think of the type of symmetry that you kind of learn about in advanced algebra. If you fold along the y-axis, that graph will line up exactly with itself. It has line symmetry for sure. So parabolas are something usually we think about when we talk about line symmetry, which they actually call it the line of symmetry. Now, what I'm asking though is it point symmetric as well? Is there a point where it's symmetric with respect to? Most people guess if there's going to be a point it has symmetry with, they guess the vertex. Kind of an important point on a parabola, but that would mean if you pick a point on a branch and you draw a line segment through the midpoint, you'd have to have a point equal distant on other side. Well, there aren't any points over there, so it can't be the vertex. All right, well, how about a point in the inside then? We kind of said they should be in the middle, so let's just pick a point in the middle. If you take a point over here on one branch, having that as my midpoint, can I draw a line segment through and find a point equal distant on the other side? Well, it might look like it for that point, for that one particular pair, but to be symmetric, it has to work for all of them. So what about the vertex? What if that's my point number 1? If you draw a line segment through the midpoint, are you going to find a point 2 equal distant on the other side? No, there aren't any other points there. So this one does not have point symmetry. So it is not symmetric with respect to a point. So it only has line symmetry, not point symmetry as well. Okay, last one to look at for graphs for right now is a line. So think about a linear situation. If you have a line, is there a place that you can put a point of symmetry, an M, where there's points equal distant on each side? Well, think about it. I'm just going to pick one. Say I say this is my point M. Is there a way that I can take a point number 1 on one side and draw a line segment through and find a point equal distant on the other side? Well, sure. And you could do that with any point on that line would be equal distance from M. But where else could M be? What if I picked M up here? Would I be able to do the same thing and find a point equal distance on both sides? Sure. So actually, lines have how many symmetry points? Any point on the line, so infinitely many. So it's symmetric with respect to any point on the line. So lines are kind of special that way. They have infinitely many symmetry points. Now, when you think about graphs, the most common point that we think of when we talk about graphing is the origin. So what we're going to talk about for our last couple pieces here today is what does it mean to have symmetry with respect to the origin? So that very special point on a graph. And the definition is just this. If you have the point x comma y, so any given ordered pair, then if it has origin symmetry, that graph, you have to have the point opposite of x opposite of y as well. So the x and the y both change sign. Let me show you an example of that. So if you have like a set of ordered pairs, a table of values, could you look to check for origin symmetry? Well, just look at the point. That first point is 2, 3. So I'm going to go ahead and graph that. That's in quadrant 1. If the origin is supposed to be our point of symmetry, so this is our M, that means if we draw a line segment from the point that we started with, equal distant on the other side, we should find that point as well. Well, what does it look like the coordinates of that point would be? Over and down looks like -2, -3, equal distance. That's what origin symmetry means. Well, that's just opposite of x, opposite of y. So if I start off in quadrant 1, I should end up in quadrant 3. Let's try another one. So what if you're starting off with a point -4, 5? So that's in quadrant 2. Now, same idea. If I'm going to use the origin as my point of symmetry and I'm going to go equal distant on the other side, where would I end up? Well, what does that ordered pair look like? Looks like +4, -5. Look what happens. +4, -5, I have opposite of x, opposite of y. So origin symmetry just means they are equal distant. That means it's going to have to be on the opposite side of the origin, same distance. So both the x and the y change sign. Now think about a regular graph though. We're just doing like a set of ordered pairs idea here. Just here are a few ordered pairs. What if you have in a whole equation an entire set of points like a parabola or a line or a circle and you have infinitely many points? How would you prove origin symmetry? Well, if you're going to do it this way, you'd have to do every single ordered pair on the graph. That would take forever and it'd be really sad because you'd never finish. There's infinitely many points on those graphs. So we can do the same idea, but with the function rule instead to prove origin symmetry. So we can actually use the function rule f of x has symmetry with respect to the origin if and only if this is true. If you take f of negative x or opposite of x, that has to be equal to the opposite of f of x. Now what that means is, inside here, if the x changes sign, then over here, what does f of x mean? Well, that's the same as y, right? So opposite of y, the y has to change sign as well. So both the x and the y are changing sign. All right, so I'm going to have you use your graphing calculator here. Can you please graph 1 over x on your graphing calculator? And I would like you to make a sketch of what that graph looks like. So go ahead and pause the video if you need to and make that graph. All right, so when I put in 1 over x, on my graphing calculator so I can see that picture, you're going to end up seeing some asymptotes and things because there's some places that it is undefined. So when I plug in my 1 over x, what is my undefined place? What is my excluded value on this graph? Well, what can't x be? Well, it can't be 0. So on my graph, I'm going to go ahead and show that with a dashed line to show that asymptote. It gets closer and closer, doesn't quite get there. Let's talk about the x-axis for a second. Can 1 over x ever be 0? Well, think of even bigger and bigger numbers for x. 1 over a billion, 1 over 10 billion, 1 over 50 billion. It gets smaller and smaller and smaller, never hit 0 either. So that's another asymptote. It's a horizontal one. We're going to talk more about that. If you want to see some places where you have ordered pairs that are solutions, just go into your table. So you can see some ordered pairs that you have there, but let's get some points on here. I had 1, 1, negative 1, negative 1. You can get some other ones like 2, 1/2. Just get enough so you can see what that shape looks like. So it's in quadrant 1 and quadrant 3. Definitely a function. What kind of function? Would it be continuous or discontinuous? Well, it's discontinuous because you'd have to lift your pen or pencil, but definitely a function. Now, does it look like to you that it has origin symmetry? If you take any point on the graph, if you draw a line segment through the origin, do you find a point equidistant on the other side? Sure looks like it to me, and we can look at those points. 1, 1, negative 1, negative 1. That's like x, y, opposite of x, opposite of y, which is great, but there's infinitely many points on this graph. We have to be able to prove it. So here's how we prove it. We go back to our rule. F of negative x has to equal opposite of f of x. So I need to show that those two statements are equal if I'm going to prove origin symmetry. So just plug in your rule and try it. So I'm going to plug in opposite of x, and I'm going to take the opposite of the whole thing. When I look at that rule, they both simplify to exactly the same thing. What does that tell me? That they're equal? That means it does have symmetry with respect to the origin. It's a great way to show it for all of them. If the x changes sign, the y has to as well. Okay, let's try another graph like that. Go ahead and graph this on your graphing calculator. So go ahead and pause if you need to. Graph that equation. So it's going through the point 0, 0, 1, 1, negative 1, negative 1, 2, 32, so way too big. You get a shape that looks something like this. Does that have symmetry with respect to the origin? Well, it sure looks like it to me again, because look at those points. 1, 1, negative 1, negative 1. It looks like we're going to have that relationship again. But just like the last one, there's infinitely many points on this graph. I have to show that this relationship is true. So let's try it. So plug in an opposite of x and take the opposite of the whole thing. Now, I know that the parentheses are different and they're meant to be. We're putting in a negative x or opposite of x, and we're taking the opposite of the whole thing. But just like the last one, those two expressions, they're equal. So what does that mean? It's symmetric with respect to the origin. So we're checking to see that. All right, now what happens if you take parent graphs like x to the 5th and you do some translations? This is what I'd like you to look at. If you graphed x to the 5th plus 7, what does that do to your graph? What does a plus 7 do? Okay, make a sketch of that. Check it on your calculator if you need to. So pause if you need to. We're going to go up 7. That means 1, 1 would go up to 1, 8. Negative 1 would go up to 6. And we get our new graph. Now take a look at that. Does that graph still have symmetry? Sure looks like it to me, but it's not the origin anymore. You're not drawing a line segment through the origin. What happens to your symmetry point? Well, it looks like it's going up 7 along with the graph. So our new point of symmetry, it's symmetric with respect to the point 0, 7, not the origin. So the moral of this story here is make sure you realize if you're translating your graph, if you're moving it around, that could affect where your symmetries are. So we need to really keep that in mind. So the graph is still symmetric, just a different symmetry point. Okay, our last one, let's take a look at this function. F of x equals, and that quadratic. So it's degree 2, so that means it's a parabola shape. So hopefully every time you look at a graph, you know what that's talking about. Parabolas have what kind of symmetry? You fold them this way, so that means it would be line symmetry. So I know we already did an example of this, that it's not symmetric with respect to a point. There's no place you can put the point. So the origin is a point. It's the short answer to this, it's going to have to be no, because we know what parabolas look like. However, once again, if you're going to actually prove it, if you're going to actually show it, you need to make sure that this relationship is not true. So we're checking to see if that's equality. So let's try it. Put in an opposite of x. And then we're going to take the opposite of the whole function and see if they're equal. So that would be positive x squared plus 2x minus 1. Over here, remember the minus goes to everything. And are those two expressions equal? No, they're not. So what that means is it's not symmetric with respect to the origin. Again, if you know what the equation looks like, you should have a gut feel about that, but we need to be able to prove it. So what we talked about today is point symmetry, and most specifically what it means to be symmetric with respect to the origin.